we're privileged to have Henrik Stiesdal, Siemens Wind Power Chief Technology Officer, at the lectern. For my time in writing on renewable energy, I would suggest there is no one better to speak on the topic of offshore wind's potential to challenge for a place as one of the world's primary energy sources in the not-too-distant future. Henrik is a pioneer. Now, the word is used rather liberally these days, but in his case, it is wholly appropriate. Henrik's first fully fledged wind turbine was a 3-meter rotor diameter machine, hand-built with his father in 1978. Yes? 6. More importantly, it was made from bits salvaged from a scrapyard outside his hometown in Brande, Denmark, and transported out to the fields behind his family farm for testing on the back of a wagon. Now, that first turbine has been instrumental in the creation of the so-called Danish concept designs, 3-bladed machines we have come to see as synonymous with wind energy, and launched Henrik into a trailblazing career in wind power technology. In 1979, Henrik and his business partner, Karl Jorgensen, sold a first 30-kilowatt design to the company that would become Vestas. Of course, the rest is history, but history is still being written. Today, 35 years on, the giant 6-megawatt offshore turbines he devised for Siemens are being installed for the first time en masse off the UK at the westernmost Rough wind farm. And there's even a 10-megawatt model waiting on the drawing board for the market conditions to be right, or so Siemens Wind Power Chief Executive Markus Tacke recently confirmed. Henrik? Yeah? Okay. Henrik has been a revolutionary influence on just about every nut and bolt developed for the modern wind turbine. From the blade manufacturing concept, now known as integral blade, to ultra-high output direct drive transmission systems, and even novel jacket foundation designs, Henrik is changing the way the industry thinks about its technology and the way we all think about energy. As Henrik once said to me in an interview, what is clear is that when I think about the world's need for clean power, I can find no other discipline that has the same feeling of potentially providing the answer to this than we have in wind power. And now offshore is clearly where we must go. For his contributions to the global wind power industry, and it should be noted, at least in passing, that Henrik has more than 200 patents to his name. Henrik has been widely laureled, including Siemens' top innovator Gong in 2010, and in 2011, the prestigious Polarcor Prize, awarded by the European Wind Energy Association for outstanding achievements in the field. Ladies and gentlemen, I now turn this evening's proceedings over to the Carbon Trust Chief Executive, Tom DeLay, who would like to offer a few remarks before Henrik presents the Carbon Trust 2014 Innovation Lecture entitled Innovate to Generate, How Offshore Wind can become a truly global energy source.
Thank you, Darius. And thank you to everybody for coming along this evening. We really value you taking time in your diaries to come along to what I believe is going to be an absolutely fabulous lecture. I was never a great engineer, but I recognize that many other people have been. Henrik is just inspirational. I've seen what he's been doing, and I'm just delighted that he's here. So thank you on behalf of the Carbon Trust and its board for coming to join us this evening and deliver the first inaugural innovation lecture that we've done. We've done lectures around other things, around policies, markets, but we think innovation is really, really important, so we want to really put it up centre stage. I'm going to talk very, very briefly. For those of you who are not aware of the Carbon Trust, we're an organisation that's been around for about 12 years as a bridge between government and business in the UK initially. But we're now a fully fledged and independent organisation, a not-for-profit, at least in US parlance. And we work in a number of areas with offices in Beijing, recently in Mexico City. We just put our first office there. We've got a presence on the ground in South Africa, but really we're based here still very much in London. We do a couple of things. We provide advice to businesses, governments and public sector organisations of all kinds of scales and around the world. We do an awful lot of environmental impact assessment and measurement. We do footprinting of organisations, products, services and supply chains. But at the heart of it, we also recognise the need for innovation in what is our mission, and therefore we develop and deploy low-carbon technologies. And we've been doing that now for well over a decade, everything from early-stage venture capital through private equity interests that we have, through to big innovation programs, the biggest single innovation program of which is the Offshore Wind Accelerator. So why did we end up as the Offshore Wind Accelerator? Well, we absolutely recognise the role of offshore wind as being central to our mission. So, that was really important to us. But we also recognised the challenges offshore wind was going to face in terms of cost reduction. And that somehow we needed to harness an industry to make this happen. And we thought, well, what role can we play? We're a very small organisation, about 180 people. But we can be a catalyst to much bigger organisations if we can bring them together and make things happen. So we saw this opportunity maybe to develop almost a sort of an R&D club amongst the developer community. And that's where the Offshore Wind Accelerator started. It's been around for 5 years. It's funded 1/3 by the Department of Energy and Climate Change here in the UK, 2/3 by the industry partners, to a total of about £60 million. Now, what's interesting, of course, is it offers great leverage. Collaboration is great because it allows you to share both costs and expertise, and there's really value in both. It's expensive enough trying to develop a technology alone. If you can somehow mitigate that by sharing the cost, it's really valuable. It offers 2-to-1 leverage of public funding. But importantly, to the developers who partake in this, because there's 9 of them, they get actually £14 of R&D value for every £1 they put in. So it's actually a really good way of leveraging the great skills and capabilities of an industry. The 9 partners represent pretty much 70% of the round 3 consented sites here in the UK. So that gives some scale of kind of it's real and it pretty much is inclusive. So what else has it done? It's focused in 4 areas, and those are 4 areas where we felt, look, the industry really just wants solutions. There are IP plays and there are commercial interests, but at the end of the day, the developers in the industry simply want solutions. Access platforms, getting access onto the offshore structures so that you can extend the operating part of the year, as it were, and actually maximize the number of days in which you can absolutely get access in the most hazardous and difficult of North Sea conditions. We also recognize the need to look at the yield potential of wake effects and really drive that. And some years back, it was remarkably primitive. And now, of course, it's a lot more sophisticated than it was then. So we started looking at wake effects. We recognize the value of very high voltage electrical systems and real step change in that and what that would do to the costs in the industry. And lastly, we recognise the need for foundations. And there's going to be a bit of a talk later on about sort of foundations. We started putting together innovative foundation concepts through competitions and then actually putting them out there in the water, first as novel bits of manufacturing and design, then something that you could actually put a met mast on, and finally we're in the position now where we're seeing novel foundation designs going in with turbines on top. And that, of course, is the integrated operation that we're all seeking to see. And it also opens up an interesting question, should we be collaborating not only in a UK context, but more broadly across Northern Europe? I personally believe that it is very much in our collective interest to collaborate more broadly outside the UK and across Northern Europe. I think it's a great opportunity, and I think every way in which we can make that happen, we should promote. I was delighted actually to hear that the last foundation prototype we put in place is actually going into a dong installation in German territorial waters. That to me is just indicative of the collaboration. We needed somewhere relatively quickly to actually demonstrate a piece of technology that was coming along, and we managed to make it happen in that way. So what kind of impact do we think that's had? Well, of course, the answer is only part of the solution. We believe we've identified just over 15% cost reduction potential across the whole of the offshore wind system, as it were. About 2/3 of that, we believe, will be available for round 3, and the last third is probably going to be sort of beyond that. But we recognise that 15.5% is really only part of the story, and there's an awful lot more to be reached out for. And that's where, I think Henrik will give us now an overview that very, very few people can provide. So I've talked enough about the Carbon Trust. Thank you very much for your time this evening in coming along. Thank you, Henrik, for coming along, and I'm going to hand over to you now.
Siemens Wind Power, the company that acquired Bonus Energy 10 years ago. It's now a 5 billion company, and this is a bit about what it has been doing in the offshore market. We built the first offshore wind farm ever back in 91. It's almost to the day, the 23rd year anniversary of the inauguration of the wind farm. Started producing power on the 13th of July 91. but we inaugurated, I think, on the 16th of September. We have installed about 1,700 turbines through the life of the company Offshore. All of which, by the way, are, of course, there are some that are still in commissioning, but all that have been commissioned are in operation. And here's a brief overview of the history. The result that we see here comes out of a dedicated strategy that we made back in 1989. I worked in a company that had lived through the roller coaster days of the California market. And when you had done that and survived, in many cases your perspective was not further from your nose than this, because the future just looked like something that was incredibly uncertain. But we did make a couple of strategic decisions, one of which was offshore wind. Because in 1989 it became clear that the Danish government would be sending out 2 demonstration projects. And at that time we said to each other, we need the first. Because it will be something that nobody else can ever match, logically. We needed to have that. We went for it. We even actually had a profit on it, even though it was a strategic project. And it was wonderful, and of course also a little bit chilling the day we signed the contract. We said, okay, so now we're actually going to do something that nobody ever did before. But it actually worked. It, like so many other tasks of that nature, is just about breaking it down into manageable parts. And in some ways we kind of cheated. When we did the installation, there was of course nowhere to look because nobody had done offshore wind. We said, maybe we should also not be the first to do offshore wind. So we actually told the crane driver, whose name is very much Viking name, Leif. We said, Leif, you're going to install some turbines, 11 of them. We're going to drive you onto a barge with your crane. And it'll be kind of blue. But you just pretend it's green. So it's like in an ordinary day at work, Leif, go out and do it. And then Leif went out. And I don't know if in his mental picture it was green, but he certainly did it at the same speed as he installed onshore turbines. You can't do that in the North Sea, but in the Baltic it was definitely doable. Then Middelgrunden, which was the first larger project. In 91, when we did the first, we said to each other, it'll be another 10 years. It's good we have this one here, but there will be 10 years. In actual fact, there was 9 years, so it was not so far off. To Middelgrunden, this very much photographed project outside Copenhagen. One of the first ones that is powering a big city like London Array is. And then on to Nysted, the very first 100 plus megawatt project. Greater Gabbard, and latest last year we inaugurated London Array, 630 megawatts. I think one of the less visible but really important factors in the industry was that there was a company that was stable, that was always there and could help brush over when there were technical issues out there. And this is the development of the equipment from our first land turbine in 1980 to the first offshore turbine in 91, 35 meters diameter, 450 kilowatts, and to what will be our workhorse of the future, the 6 megawatt. The aircraft up there on the figure is the biggest aircraft in the world, the Airbus A380. So it is really big equipment. Great fun for engineers, sometimes a little chilling for you as a business person when you look at it and say, The biggest of a lot of things in the world is exciting, but you also need to have really, really good control over your risk. I think fundamentally, in many ways, the technical part of the industry has got there. We are able to manufacture hundreds of turbines for big projects. We are able to make them so that they are reliable and can be serviced and can last for a long time. All the 11 Vindeby turbines, now 23 years old, are still operating. It is doable. But of course we have the big challenge on the cost. And that is one of the key drivers, because ultimately our innovation activities are founded in the need to bring down cost. And in that context we speak about levelized cost of electricity. And I'll just very briefly explain that. I think most of us have a pretty good fingertip feeling, but still. And this is of course what it's about. It's the cost per energy. That's a fundamental formula. But we do use the term levelized. With levelized we mean that we discount our costs and our earnings. In other words, we look at the net present value. And that makes the actual formula look a little more complicated, because it looks like this. It is not complicated at all. You just need to get your mathematics scare out of your blood. It's the sum of all the investments, and what is under the line at the investments is the discounting. In other words, money we spend 10 years from now don't have the same value today as in 10 years. And then we have the same for the operating cost, and for the investments, the discounting doesn't really matter. We spend almost all the money up front, so it has today's value. But for the operation and maintenance, it does matter when you look at the cost picture that some of the cost is spent out there. And if we have the money now, we can put them in the bank, and when we get to spend them out there, we have more money because we had an interest and so on. And oh, yeah, fuel, that doesn't apply to us. And the same applies to the energy output. And this is actually a very useful formula, because first of all, we need to know what we are talking about. This is levelized cost of electricity. I didn't cook up the formula. That's the one any power station owner will use when he considers a new investment. But it's also actually a formula you can calculate with, and we can just do a mental example. It will require a little bit of focusing, but you'll manage. At 6 megawatt turbine produces 25 million kilowatt hours, and it lives for a bit less than 25 years. It cannot live for 25 years because then you have other depreciation rules in the UK, so I need to be a little careful. It lives for a bit less than 25, sufficiently less than 25 years. So one could assume that the energy would be, value of the energy would be 25 years times 25 million kilowatt hours, in other words, 625 million kilowatt hours. But when we do the discounting, it isn't, because the energy that's generated out there in time doesn't have the same value today. And the interest rate you use for that, what's called WACC, weighted average capital cost, it's simply a word for the average interest rate, is 7%. When you use a 7% interest rate, the total today's value of the energy is not 625 million, it's 300 million kilowatt hours. Now that's actually a good figure to use, because we can look at our equation, then we say, well, if our levelized cost of electricity was, let's say, 10 pence per kilowatt hour, and then we simply move what is under the line, the 300 million kilowatt hours, to the other side and multiply, then we get 10 pence per kilowatt hour multiplied with 300 million kilowatt hours. In other words, the total cost can be 30 million pounds, 0.1 times 300. We also know, those of us who work with offshore wind, that operation and maintenance is about a quarter of the overall levelized cost. And therefore we know that a turbine would be able to produce electricity at 10 pence a kilowatt hour if the total installed cost were 22.5 million pounds. In that way, it's a useful formula. It's also a little chilling, because we know that the installed cost is not 22.5 million pounds, it's higher. And therefore, that gets us to the question of what is our challenge? And our challenge is the cost of wind. This is how the cost of wind developed in all the years of the company when it was independent, in other words, before Siemens bought it. And as you can see, it's a nice straight line in a semi-log plot, linear x-axis, logarithmic y-axis. It's an exponential decrease, 5% per year. That's what the company did. Then Siemens bought it, and prices went up. Big corporations and so on. In actual fact, it's because from 2005, the whole technical industry in the world had a boom period that ended spectacularly, as we all know, with the crash of 2008. And now we are kind of getting there again. And this is the corresponding figure for offshore wind. The green curve that represents onshore wind is turbine types, but the blue curve is project specific. And this is the cost of energy from Vindeby, Middelgrunden, Nysted, and then a generic UK North Sea offshore project in 2010. And that's not such a good development. Our reference is this. The brown curve is the spot price on the European electricity exchange. It's a kind of like a stock market for electricity that is in Leipzig in Germany. And for some years around 2005, we kind of felt, well, now we are getting there. But as you can see, after the crisis, prices went down again. If we want to project about the future, this is my projection. It will not be true. But nobody can project better than me or a chimpanzee for that matter. And the logic is very simple. It's like if we go outside today, or had done that, and said, what will the weather be tomorrow? And we didn't have any meteorological person nearby, then the best bet is it'll be like today. Works 60% of the times. That's how you impress mothers-in-law and so on. But this is at least a prediction that is as good as any. So if we want to match the wholesale spot price, then, and if we do business as usual with our 5% per year, then this is how it will be. We will be with our 5% per year roughly equal in 2020 and quite far from equal on offshore, not until 2040. That is our business as usual scenario. And that's of course not how we exactly would like it. On the other hand, we also need to note that my reference here is the spot market price that is artificially driven down by feed-in arrangements for solar in Germany, by cheap lignite prices in Germany and so on. The actual generating cost, if you were to build new capacity, is quite a lot higher. The promise the industry has made to the UK government and actually also to the German government is there will be a 10 pence in the UK, cents in Germany. There's nothing magic about the figure, or rather there is a little bit magic. There's nothing scientific, but politicians like to speak about single-digit numbers. They hate double-digit numbers for energy prices. So we need to be below 10 cents. Then you can see that still leaves a good gap. But when we look at that, we need to consider, are we actually comparing like for like? And in order to look at how we actually do that in a competent or informed manner, we have internally in my company looked at a concept that I call society's cost of electricity. So far we spoke about levelized cost of electricity, something that bookkeepers invented for us. But if we actually look at it for society, there are a number of factors that do not enter the levelized cost of electricity. You'll remember it was about the investment, about the service cost, about the fuel cost, and about the energy you get out. But they are not the only factors in life. If you take the elements of society's cost of electricity, first of all, we have what I think of as the ex-works price. And that is actually more than what we had in the equation before, because it's also the price of CO2 for those energy sources that should be penalized by a markup due to CO2. Then on top of that, we have the cost for society of the hidden subsidies. They are not small. When the UK is contracting a big European entity to build nuclear power, one of the things it has in that story is a 35-year fixed price arrangement, fixed feed-in arrangement. The wind industry would give one arm and one leg minimum to have a 35-year fixed price arrangement. It is a clear-cut subsidy. The fact that society is expected to take the insurance and pay for the cleanup is another subsidy. If you have VAT exemption for fossil fuels, it's a clear-cut subsidy. Then we have the transmission costs. That's mainly something that penalizes offshore wind. And here we need to have it all in. It doesn't work, of course, that I only speak about those things that penalize fossils. We also need to speak about those things that affect wind or solar. And it does affect us negatively that we are not centrally located. We're located in the North Sea and we need a land connection, and from there needs to be transmission, and there's a cost in that. We are also affected negatively by the cost of the cost needed to compensate for wind not being there all the time. There's not always wind that perfectly matches the load on the grid. So there needs to be backup, classically with gas turbines. That has a cost. So if we add up all those costs, we get to the true cost or the system cost of the electricity, not the ex-works, but the system cost. And then there are some other factors. There's a kind of like a social impact. In some countries, should we actually pay, does property values go down? Do they go down if you have onshore wind turbines nearby? Does the property value go down if you build a nuclear power plant nearby? And then there's the very, very important factor of job creation. Because the jobs created by various sources are within a very wide range. And finally, there's the geopolitical impact. The fact that if you are a gas customer, Putin has his hand on the valve, at least on the continent. Is that really nice? Of course not. It has a price. And that gets us to the total price. And we have done that calculation for the UK to see how does it actually look. And this is how it looks. So if you take the nuclear, the levelized cost of electricity from both the CAPEX, the bluish one, and the green one, which is the operation and maintenance for coal, no, for fuel, sorry. For coal, we have the O&M, we have the fuel, and we have the CO2 tax and so on. You can take all of them. Then we get a total LCOE, levelized cost of electricity. And then we can add the subsidies, huge for nuclear, the transmission cost, quite big for wind and solar. The variability, there's a little bit for nuclear because you need some gas backup for a nuclear power plant. There's nothing for gas because it is the backup. And there's quite a lot for wind. In that way you get to the system cost. And then when you take into account the employment effects, you can see that nuclear actually has a quite positive employment effect. It takes forever to build a nuclear power plant. So, but the biggest employment benefits are on PV and offshore wind. And all in all, society's cost of electricity looks very different from the public picture that, oh, wind is so expensive. For society, it is not. The cheapest source of electricity for society in 2020 will be onshore wind. But we can't fill the country with wind turbines. The second cheapest is offshore. Now this is not some cooked up figures. We have used public figures from the UK government. We have used where they did not publish figures. One of the big four accounting companies' figures. It is something that has been vetted by the not always, shall we say, sympathetic people in Siemens that work with other electricity sources. That's you have to do, of course. And ultimately, we've used the best sources of information. So that argument, it is valid. Whether you can actually put it forward in society remains a good question. Will people listen? Sometimes you can doubt because what the reaction will, well, we make a counter report and then some doubt has been made and so on. But this is, to the best of my knowledge, what is the fact of the case. It assumes that we can do offshore wind at 100 euros per megawatt hour. That corresponds to 10 cents. Today, as you saw on the figure, maybe it's 14. So we need to get down to 10 and hopefully lower by 2020. If we look at our equation, to get down there, we need to reduce the investment, first part. We need to reduce the O&M cost, and we need to increase the energy output. That's how we get this figure down. And this is how it's composed for a big offshore wind farm, 3.6 megawatt turbines. That is the mixture. 73% is capital, 27% is operation and maintenance. Out of that, the wind turbine is 32%. What I built for this activity has a value of 1/3 of the total cost. In other words, if I want to do the cost reduction by saving on the wind turbine, I can only get down to 10 cents by giving it away for free. If we look at our identity, I work for a wind turbine company. A wind turbine company basically has its identity from making what is on top of the tower. We don't make towers. We do make blades, but there are companies that call themselves wind turbine manufacturers, and there are wind turbine manufacturers that don't make blades. Your identity is in the nacelle. The nacelle, where our identity sits, is out there. It's 6%. I can cost out from now and to eternity. I will never ever get the cost down by that. So therefore you need to think big. And therefore you need to look at the various elements. And this is the baseline, 14.5 cents today, composed of the bluish part of there, the turbine, the civils, the electricals, and the operation and maintenance. And there we need to take down cost on all bits of that to get down to our cost target. And then on top of that, we need to increase the energy output. And that means we need to look at the wind turbine, the foundation, the grid, the OPEX, and the energy production. If we start with the wind turbine, this is our workhorse, the 6 megawatt. If we take off the dress, it's like that. It's got everything up in the nacelle. That's one of the tricks you use, that you say it has to have everything in the nacelle, because then you can commission it on the quay side. If you have stuff in the tower, you can't. The turbine is only complete when it goes out there. If it's got everything in the nacelle, you do the commissioning on the quay side. These are a few of the facts. The blade, 75 meters long, 25 tons of fiberglass. When you stand on one end, a person at the other end is that big. You should, if you ever get the opportunity, you should get close to one. The root bending moment of such a blade is 20,000 kilonewton meter. That probably doesn't mean a word to you. So you can use an older term, ton meters. That's what crane people think in. It's 2,000 ton meters, just divide by 10. If I want to load that blade with my old car, I used to have a Volkswagen Golf car. It has the big beauty that it weighs exactly 1 ton. I get nowhere by just placing it on the blade tip. If I want to load the blade, I need to put my car at a beam that's 2 kilometers long. Put the car at one end, try to hold the other. That's what the blade does. That's the load the blade sees. And then there are the other figures. You can see that yourself. I sometimes show people around in Brande and demonstrate and explain and talk like I do here. And what really captures people, see, oh, that did not work. Is there a pointer? No, there isn't. What really captures people, sorry, cameraman, what really captures people is a cafe table. Because when you are a utility person, you need somewhere where the utility people can sit down and play cards and drink coffee when the supervisor is not around. So that really hits the mark with them. To get the cost of that down, the usual stuff, the non-sexy, relentless cost out, industrialization, looking for serial production, always looking at better purchasing prices. And then, of course, the value chain view, that engineers in tendency think of their own little sphere. So the people that build the turbine think of the turbine, but they should think of the turbine installed. We need to think of the whole value chain. The next big part of is the foundation. Now, we don't do foundations today. This is outside our sphere. But we have to observe that at Vindeby, the turbine was 2/3 of the capital cost. For a modern wind farm, it's 1/3. So the wind turbine manufacturers actually delivered on the cost out, but the rest of the system did not. That's how it is. And then we need to do something about that. And the only way we can do something about it, that is to engage, is to do something where we say, we think there are things we know better than you. Because wind turbine factories actually handle a lot of equipment in a very efficient manner. Where I work in my everyday in Brande, we have 2,000 tons of turbines coming out every week. We don't manufacture 2,000 tons of stuff. We just assemble it, but we do that really, really efficiently. And this is what you could do on a foundation. This is what we have developed. A bolt-together foundation where we basically use the thinking of a wind turbine. Such a jacket foundation has legs. We actually manufacture or use thousands of legs every year. We just call them tower sections, but they could be used as legs. And then it has the nodes. They are the bluish stuff there on the legs, where the corner members meet the lattice. We manufacture thousands of nodes every year. We don't call them nodes. We call them wind turbine hubs, where the blades go on. But they are essentially the same thing. Could you not do such a bolt-together foundation? This is simply saying, if we want to do this, it has to move to a completely different level than where we are today. Because where we are today, a really good shipyard, really top-notch, can on a good run produce 1 jacket foundation a week, 45 a year. If we want to do 5,000 megawatts with 5 megawatt turbines, we need 1,000 a year. There are not 20 shipyards in Europe that can do those. It's simply will become a huge bottleneck. You need to be able to do them not one a week, but one a day, like when you install a turbine. And that is the logic of this foundation. And this is a predicted cost reduction for an installed ready foundation for a 6 megawatt. Take out 40%. We are not going to build foundations. We are going to design them and demonstrate them, and then most likely we will say to society, well, why don't you use this? Instead of saying, oh, we need all the IP, we will protect it. I think that's the best way forward. If you look at the grid, what we do nowadays doesn't work. This is what we do nowadays. It's a monster. It's grotesque. If you build a 300 megawatt wind farm, you pay 75, 80, 85 million euros for your substation. What the substation does is to transform from the wind farm voltage level and to the export cable voltage level from 33 or 66 to 150 or 220 kilovolts. The thing that does the work is the transformer. The transformer does not cost 80 million. A 300 megawatt transformer costs 3. The reason for the big difference is that then engineers take over. Then we need a meeting room, but then we need fire extinguishers, but then we need a helicopter platform, but then we need, oh, now it gets interesting. And then the snowball runs. There you need to think really radical. And the interesting thing about what we have been speaking about so far is that, and I really like the term innovation, but I'm not sure everybody, certainly not in my everyday ambience, everybody understands. Innovation is not invention. Invention is where you get your patent. Innovation is something different. Innovation is taking known technologies and applying them industrially in a way that creates value for the company and for the customer. It's not inventing stuff, it's just doing things in a smarter way. But to do that, you really need to think kind of out of the box. And the term I use internally is that I say, why not? And I also look for the radical solution. When we made blades that have no glue joints, it was because we had a lot of problems with glue joints, and the ultimate solution to glue joint problems is not to have them. When you do, as the wind industry had for many years issues with gearboxes, the radical solution to that is not to have a gearbox. And similarly here, the radical solution is not to have a transformer platform at all. And this is what we are developing, a turbine-mounted pad. No helicopter platform, no meeting room, no fire extinguishing. Just a simple, super simple arrangement where we say only those parts that do the work are allowed in. Everything else should be left out. And this is how a wind farm, a 1,000 megawatt wind farm could look. Four elements of the wind farm, each of them having one master turbine, and that master turbine ships power to shore. OPEX. The fundamental answer is robustness. We simply need to get that part of the OPEX, the operation and maintenance, that has to do with finding faults and correcting them, to eliminate that. Turbines have been made that work like that. Not now, because they're much more complicated now, but in the 1930s, a large part of the American Midwest was electrified with wind. Hundreds of thousands of electricity generating 48-volt wind turbines were installed out there, and they were extremely robust. The most robust being a famous brand called Jacobs. And one of the stories about the Jacobs turbines' robustness was that a famous explorer called Mr. Byrd from America, he created an expedition station on Antarctica in 1934. And he wanted electricity, so he installed a turbine. And then he left it again in 1935, and it was abandoned for the next 20 years, then was rediscovered. And what they discovered was that the turbine was still running and still producing power for the batteries. 20 years on its own in the most hostile environment in the world. That's the sort of turbine I would like to build. It's not that easy anymore, because it was super simple, direct drive, direct current machine. But that is where we need to get to. Have redundant systems, simple monitoring, safe access under heavier sea state than we can do now, and then of course long service intervals. 20 years ago, turbines were serviced twice a year. Nowadays they are serviced once a year, and in a few years I hope we can get to a 2-year service interval. And then finally, the annual energy production. the whole trick is, of course, to upgrade. That's what we always did in the wind industry. Our turbines always grew. And they grew by two things, either incrementally making your turbine do a little more, or taking the next step. And through all that sequence, which covers 35 years, the cost of electricity always got down. A number of times on the way we said, now it can't get any bigger. Now we are there. Now it's done, period. But it always worked to make them bigger. And in round figures, it matters more to increase power than to increase rotor diameter when you are offshore. It always worked like that. If we look at the technology when we move forward, where we will be going in the long run is to, of course, the direct drive turbines. We will have the tailored redundancy. With that I mean that the turbines are redundant in a way that keep them running even when something happens. The 6 megawatt turbine has two separate circuits in the generator and two separate power converters. Have a fault in the machine, you can still run at half power. And on energy, it will produce about 2/3 of the energy of a full machine. And then I think that ultimately electrical and civil will get down to 40% of today's cost. Our initial target is to reduce by 40%. I think we'll end up reducing by 60%. The next big turbine, once you go bigger than something, once you go bigger than a few megawatts, then you essentially use the same equipment out there. So it really pays to have as big a machine as possible. And the next machine will have a direct drive generator and will look basically like the machines look nowadays. And these are the figures: 10 megawatts, 210 meters diameter. That's a big blade. It will weigh 55 tons. 50 million kilowatt hours a year. My family, I have 2 teenage daughters and a baking wife. I don't know how to say that, but you know, she makes bread. We use 4,000 kilowatt hours a year. So one turbine could power 12,000 families like mine. When it works, it takes 420 tons of air through the rotor every second. And in 5 days, at 5 average days, it will produce as much as the company's first turbine did in the 35 years from when it was installed and until now. And this is how it will look, or one of the variants we are looking at. And that's really fun. That's thrilling to work with such a machine. And this is our projected curve. There are actually 2 curves. And for a good and bad reason, you can say. The good reason is that this is how it will develop. The dotted curve is what the calculations show we could do. The blue curve is what will happen. Because one of the big constraints in offshore that's often not recognized is the inertia of the system. And very simply it's so that we have a lot of dialogue with our customers, and they find it, generally speaking, entertaining and rewarding, I hope. But it feels we have good dialogues. That works fine. But as soon as a project gets to be a project, then nobody wants to touch innovation anymore. The last thing the project manager would want is anything new, because he has to complete on time, schedule, budget, etc. So innovation stops the moment you have a name on the project. That's a very, very big hurdle on offshore. And that is where I would get to the host of tonight, Carbon Trust, with their offshore wind accelerator, and say that's one of the key initiatives to get people on board on innovation in a way that penetrates not only on the supplier side but on the customer side, so that we have an increased willingness in innovation, because it is kind of known, it happens, it's collective, there are other people doing it, we are not the only ones that are fooling around and so on. This is a really big issue for offshore wind. And among the many initiatives on the wind accelerator, you can see that the foundations are, of course, those that I kind of think of. The one on the very right is the Dong Foundation that has just been installed, which is a very important step. Dong is the most competent of all the customers, and they are very far in developing their own technologies. I don't think they will need what Siemens does, but quite a lot of other customers will probably benefit from what we are doing here. This is hugely important. Just a few figures on how the world looks. This is new capacity cost in Denmark today, calculated not by me, but by the Danish Energy Agency, an organization under the Department of Energy. The cheapest electricity you can buy as new capacity in Denmark is onshore, Danish kroner, divide by 8 and you get it in pounds. Onshore wind is the cheapest new capacity you can build today. That's really fun for an old windman like me, who used to hear always, it's too expensive. That's really fun. But even offshore, you can see in Denmark, is about the same level as gas and coal when you take into account the cleaning mechanisms you need on our grid. That's really great. A few figures on Denmark, where I come from, 5.5 million people, 33% of electricity from wind in 13. 55% for the 3 winter months and 62% in January. That's also fun. I gave recently a lecture at the Danish Standard. It's a sort of entity that does standardization. 25 years ago, they created a wind group. And I gave us the speech at the anniversary. And there I mentioned that in 1989, when they started, one of the claims about wind was that wind in Denmark produced as much electricity as was needed for the electric heaters of the waterbeds of the country. Ha ha ha. That the ha 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 is not quite there anymore. We do have some waterbeds, but not with that kind of load on the grid. In January, some projects did really well. We had a single turbine that had 89% capacity factor. In other words, it ran as if it was producing rated power for 89% of the hours of the month. And one single offshore project, 400 megawatts at Anholt, produced 8% of the country's electricity needs. And this is how it looks for this year. The wind share on a monthly basis in 13, 33%. For the first 6 months of this year, 40%. It does matter. Another fun record, we recently had, for the first time in history, turbines that need now a 9-digit meter. For the first time, any turbine in the world reached 100 million kilowatt hours as total lifetime production. Of course, still running, they are 11 years old. That's cute. And then if we look at going forward, what it's all about, this is one of the curves that it's all about. It's a curve issued by the US Department of Energy Information Agency, EIA. It's a little confusing because we also have the International Energy Agency, IEA, but this is something like it. They produce curves like that. And what the curve shows is that over the years, we will have contribution for electricity from oil at the bottom, gas, coal, the big, brown, ugly blot there. Nuclear, hydro, and then that little light blue thing on the top is wind. The other energy sources grow by 2%, wind grows by 10%. But still you can see it's an abysmal impact we have. Way, way, way too low. And but what happens is that governments will say, oh, those people predict that. Well, maybe we should make policies that kind of fit to that. So it becomes a self-fulfilling prophecy. Who actually does those curves? Well, middle-aged men like me, some young people out of business school and people out of the oil and gas industry. I don't think we should be driven. I think that people like us should be driving. I think we should say, yeah, that's fine, but no. And the trick to get there is to do this innovation that we spoke about. To do it collectively so that we support each other and to say, we don't care what you say, but we will make it so that it becomes the most competitive source of electricity. And if we get there, we could get to a curve that looked like that. That is what our children will be thankful for 50 years from now, if we can do that. Your moment of zen, this is a 6 megawatt turbine. It produces, as I said, 25 million kilowatt hours. Just to put that into perspective, 1,000 of those turbines could produce all of electricity in Scotland. I just thought I would say it today because it may be the last day it has any interest for you. It has been developed in Denmark and the UK. The UK contribution is not small. Our generators are electrically designed at Sheffield University by a team we have there. And the power conversion system is designed in Kiel, up near Stoke. And for the UK waters and for many other waters in the world, they will actually be manufactured in Hull. I still call it UK, I don't know if that, but still it was a good opportunity to keep on using that. I think that's kind of okay. So can we do that? Can we actually, in my opinion, by joint effort of industry and public funded research, including not least what Carbon Trust has been doing, can we actually provide the basis for those reductions? And there I would like to return to the statement that I have used in my approach to innovation, which is very simple: why not? Thank you.